Professor Bialis here. In this video we're going to be talking about section 3.6, which is introducing the idea of functions. Up until this point we've always worked with equations. We graph them, we solve them. And now what we're going to do is kind of start shifting gears into a discussion of functions. Now it's not really that different than the equations we've been dealing with, it's just, it opens the door to different possibilities and different discussions. This section is just an introduction. So there's not going to be a lot of calculation going on so much as just understanding the terminology and understanding the notation. Whenever I say notation, it's a way of writing something. Nothing more than that. Okay, and it's very simple, very kind of scratching the surface of things, but it can really be a detriment to your understanding of the deeper concept if you don't get how things are written. Okay, I personally struggled when I went through Calc 2 and Calc 3. However, it was really just an issue of how things were being written. Once I got to grad school, I dug a little deeper into the calculus and everything started making sense once I kind of decoded how things were being written down. Okay, so it's very important that we get that down pat and we write things correctly. So keep that in mind as we're going through this section. So let's get started. Again, this is section 3.6 and we're talking about functions. Okay, now before we do any kind of number stuff, let's look at some definitions. Before I get into a function, I need to define a relation. A relation is simply a set of inputs and outputs. Okay? Now, inputs is something that you plug in somewhere, and the output is what comes out of that. Okay, now that could be a calculation, or think of a factory. Let's say I'm manufacturing baseball bats, and I have a raw piece of wood that I pump into a machine, and then it carves out that baseball bat. Okay, so your input would be that raw piece of wood, the output would be that baseball bat I get on the other side. Okay, so an example of that could be, in more of a mathematical sense, a set of ordered pairs. When we look at these ordered pairs, so set of inputs and outputs, we could also say a set of ordered pairs. One coordinate being your input, one coordinate being your output. Now, it's not whatever coordinate you want to be the input. Typically, the input is going to be your x coordinate and your output is your y coordinate. Okay, so if let's say I will look at a relation and I have 3, 5, negative 1, 0, 4, 8, negative 1, 11. That's a relation. It's a set of ordered pairs. Okay, we have inputs and outputs. I plug in a 3, I output a 5. Input a negative 1, I have an output of 0. Okay, that's all a relation is. Simple as that. Okay, now let's go into more specifics and look at a function. So a function, first and foremost, is a relation. So it's a set of ordered pairs in which every input has one unique output. Every input has one unique output. Okay, now what I mean by that is look back up here in this relation. This is a relation. It's not a function though, because this input of negative 1 can output a 0 and it can output an 11. I don't want that. Not that it doesn't ever exist, but that's not going to benefit me. Think back to that factory example. I don't want a machine. If my business is I'm making baseball bats, I'm not going to buy a machine that if I pump in a piece of wood, sometimes it'll be a baseball bat, sometimes it'll be a broomstick. We'll see. I don't want that. I want to have one unique output. Okay, so that's what makes a function. So let's say we have something like this. 3, 2, 5, 9, 7, 2, and 11, negative 13. Let's say we have that. That would be a function, because when we plug a 3 in, we will only get a 2. When we plug a 5 in, we will only get a 9. A 7 only get a 2, and so on. Okay? Now, some of you may be thinking, well, wait a minute, what about these 2's? That's okay, because if you go back to that baseball bat example, if the input's different, as long as I have a predictable output, I'm okay. If I pump in a piece of pine and I get a baseball bat, and then pump in a piece of oak and also get a baseball bat, I'm okay with that because we have baseball bats. I know what to expect on the tail end of it. Okay, so a kind of simple way of looking at this is, if I have repetition in the x's, no good, not a function. But if I have repetition in the y's, that's okay. Okay, so that is how we can determine if something's not a function or a function when it's simply a list of ordered pairs. Okay, now those ordered pairs typically aren't just listed though. A lot of times we graph those. So how can we tell if a graph is a function or not? So are these functions? And let's say I give you something like this. Just a regular line, okay? Now, what we use to determine this is called the vertical line test. Okay, so let's write that here. Now, how I like to describe that is kind of the wrong scenario. Okay, so a vertical line test says this: if I can draw a vertical line that touches the graph more than once, it is not a function. Okay? So, if I look at that graph and I draw a vertical line that hits it more than once, the answer is no. But any vertical line I can draw will only hit that once. So in this case, yes, that is a function. Okay? How about this? What if I graph a circle? Don't worry about how that came to be. We will talk about that in a later class. I just, given that graph, is it a function, yes or no? Okay, if I do a vertical line test, all it takes is one. If I can draw one vertical line that hits it more than once, no, it is not a function. Okay? Now, why? Why does that matter? Think about what a vertical line is and how we describe it. Remember, the equation of any vertical line is x equals a number. So let's say this is x equals 5. I'm just randomly picking 5, okay? So that means this ordered pair here could be something like 5, 1, and this ordered pair here could be something like 5, 7. If we look at it as ordered pairs, we have the same x, different y's, not a function. That vertical line test shows us that this situation is happening without having to pull the exact points off of it. Okay, so again, if you hit more than once, not a function. Okay, what about something like this? Let's say I have something like that. Okay. Now, that's what we call a piecewise function. You're going to see that in a later course. But, again, we can still analyze this. Is that a function, yes or no? I think the only spot that we would all agree would be questionable would be this spot right here. Okay? If I draw a vertical line, I'm hitting both of those spots. But am I hitting 2 points? Think about what that open dot is going to represent. That open dot represents a value that I get infinitely close to, but I don't include. So in this case, that open dot right there is not a point on the graph. So I'm technically only hitting 1 point, so yes, this is a function. If this right here was closed, then it would not be a function because I would be hitting 2 points at once. Okay? So we have list of ordered pairs. How do we determine if it's a function or not? We know how to do that. We have graphs, vertical line test. Let's then go, where's my eraser? Here we go. Let's then go into what usually describes a graph, which is an equation. So again, are these functions? Let's say we have y equals 2x plus 7. Okay? Now if we have 2x plus 7, think about the input-output idea. If I plug in a number, let's say we all plug in the same number. Let's say we all plug in 5. If we all multiply 5 times 2, will we get the same result? Yeah, we'll all get a 10. If we then add a 7, will we all get a 17? Yes. There's only one correct outcome or output to any given input. So in this case, yes, that's a function. Another way you can think about this is just in your head, give yourself a general graph. This is a line. Okay, we have a y-intercept of 7 and we have a slope of 2, so it's going to look something like this. Okay, so if I draw that line, I'm going to pass that vertical line test. I'm good to go. Now, what if we have something like this? What if we have a vertical line itself? Now, if we are graphing a vertical line, would that pass the vertical line test? No, because if I draw a vertical line on top of this, I'm going to intersect that an infinite number of times. So, vertical lines are not functions. What about horizontal lines? Okay, would a horizontal line, if it was, let's say, y equals 8, would that be a function? Yes. Horizontal line would pass that vertical line test. So in this case, yes. So in this section, really the only thing that's going to be a no that they would throw at you is a vertical line. Any other line would be a function. The other thing that they may throw at you, you may see it in later chapters, but I might as well introduce it here. Let's say they give you something like this. Okay. Whenever you have a y squared in an equation, no, it is not a function. And it's because of the y squared. The reason for that is if you were to solve that for y, you would eventually have to take a square root, and that square root would give rise to what's called a plus and minus sign. So there's actually 2 results for every one input, or 2 outputs for every one input. Again, right now, take my word for it, we're going to have to dig a little deeper into this in later chapters to really see the inner workings of that. Okay, now an x squared is perfectly fine. If let's say we had, x squared minus 2y equals 4, that is perfectly fine. Okay, that would be a function. Okay, so the 2 things to look out for when the answer would be no, it's not a function, would be a vertical line or when the y is squared. Okay, otherwise, typically, we got a function. Okay, there might be some exceptions later on, but again, that's when we get into more complex stuff in later courses. For right now, y squared is a no, vertical line is a no. Okay, so let's now go into another aspect of functions called domain and range. Okay. Whoops, let me erase that. Okay. Now, first of all, what are these, and then how do we figure them out? So, what are they? Domain is going to be the set of all included inputs, while range is the set of all included outputs. Okay, set of all included inputs, set of all included outputs. Now remember, inputs typically we're going to think of as x values, while outputs are the y values. Okay? So let's go back to here. Let's go back to these two lists that we have here. They don't have to be functions in order to determine domain and range. They could just be relations in general. So if we're going to this one here, if I'm looking for a domain, your domain would be all included inputs, which would be 3, -1, 4, and then we already have -1. We don't need to write it twice. We just want to say it's in the set. And there's your domain. A lot of times they'll list this in numerical order just to keep it organized, but it's not necessary. Okay, that's just to kind of keep it looking nice. Range. What are my included outputs, aka what are my y values? And in this case, I got a 5, I got a 0, I got an 8, I got an 11. Simple as that. Down here, if I look for domain, domain is 3, 5, 7, 11. What's my range? My range is 2, 9. I already have a 2, and -13. If you put the 2 twice, again, it's not wrong, but it's just saying, hey, there's a 2, hey, there's a 2. You're just saying it twice, and that's not really necessary. So that's what domain and range is. That's how we get it off of a list of ordered pairs. What about a graph? Let's say, I'm just going to give a general sketch here. Let's say I just have a line segment. I have a distinct starting and ending point on that, and I want you to tell me the domain and range. Okay? So, if I'm looking for a domain, let's say this point here is -3, -1, and let's say this is 5, 4. Okay? If I'm looking for domain, I'm looking for any included x values. Now, what I see a lot of people do is they say, well, the x values are -3 and 5. Those are just the endpoints. Even if I have a distinct line segment, there's still an infinite number of points that are on this segment. Okay? So, yes, it's -3 and 5 and everything in between. So if I'm looking for domain, I'm looking for any x values. So watch what I'm going to do here. I'm going to connect that x-axis, and I'm going to include anything in between. So my domain I can write as -3 to 5 using interval notation. I'm going to include those two values. Okay? Now what about my range? My range is going to be the same thing except it's the y values. So I'm going to connect this to the y-axis. Okay? Now what y value did I have down here? I had a -1, and up here I went as high as 4. And I have a line everywhere in between. So my range, I'm always going to go from the bottom to the top, small to large, is -1 to 4. Again, I'm including those because those circles were closed. And here is my domain and range. Okay? Let's say we have something like this. Let's say we've got and let's say this point is -2, 1. Okay? Now again, I'm not going to ask you to graph anything like this, but we have a distinct starting point, and then we go out infinitely this direction. Okay? So, how would that look in terms of domain? Domain, how far left do I go? How far right do I go? I like to start here, and let's picture someone walking on this x-axis. I don't see any graph until I hit this, and that starting value of x is the -2. So my domain is -2, and then there's graph going on forever to the right. So I would put infinity. Now, remember with interval notation, infinity is always a parenthesis just because we can't distinctly get to that point. The -2, since it's an open dot, will also have a parenthesis on it because I'm not including that value. What about range? Okay, if I look at the range, I'm starting at a y value of 1, but notice that graph is rising forever as it goes out. So my range is going to be 1 on to infinity. Again, always parenthesis there and parenthesis here because it was an open dot. And there's my domain and range. Okay? So again, guys, show this connection in between. We're going to keep it very simple. As we go further, like in 09-8 a little bit and later chapters like chapter 8, we're going to see some more complicated graphs, but right now we're going to keep it pretty simple just to get the point across. Okay? So we talked about domain and range with a list of ordered pairs, with a graph. What about an equation? Let's say I have y equals 3x plus 2. Now, when we deal with equations, all we're going to be looking for is the domain. That's it. Okay, when we find the range of something like that, we either have to graph it or we have to know something called inverse functions. Okay, we'll talk about that when we get into chapter 12 later on. So, keep it simple, just find the domain. So what x values can be used? What x values can I plug in and it still works? Maybe not nicely, but it works. What numbers can I multiply by 3? Everything. What numbers can I add a 2 to? Everything. So in this case, my domain is negative infinity to positive infinity. That's it. Okay? Now, something that will have an issue is when we get into something like this. Okay? Now, that's what's called a rational equation. You'll see that in more detail in chapter 7. But I just want to think about the domain in this case. When we're looking at the domain of something like that, we have to think, where can we have an issue? It's a fraction. What issue comes up with fractions? Not negatives. Negatives are fine. But a 0. Specifically, a 0 in the denominator. I can't have that because that will be undefined. So, when does that happen? When does that denominator equal a 0? Notice what I did. I created an equation where the denominator was equal to 0. End of story. Okay? So, I'm going to subtract, and I have x equals -7. Now, what do we do with that? That's not the number we want. That's the number we want to avoid. So that's what we cannot equal to. Okay? There's a couple ways you can write this. You can use what's called set builder notation, but they're pushing in this section interval notation. So what we want is everything except -7, like so. Okay? So if we're looking at that number line, how do we write that in interval notation? Well, I got shading here from negative infinity to -7. And then I have a shading here from -7 to infinity. Always parenthesis on infinity. And then at -7, notice I'm really getting close on the left and the right, but I'm never really touching that number. So I get really close on this side, really close on this side. And there we go. Okay, that U stands for union. You're just unifying these two separate intervals in one complete idea. Okay? So, really at this point in the game, when we talk about domain of an equation, the only thing that they're really going to be creating an issue with are these rational equations here. So set the denominator equal to 0. If it helps to graph it, and then we have that. Okay, one last thing to talk about here is function notation. Excuse me. Now, as I said before, notation simply is a way of writing something. Nothing more than that, okay? So, what we would see in the past is something like this. Find y when x is 5. And they give you something like this. Okay? Take this expression, find y when x is 5. All that means is you're plugging a 5 in for x and you're calculating. What we're going to do differently now and write differently is, instead of y equals 2x plus 1, I'm going to write it like so. Okay? Now that's not f times x. This is going to be read as the function f names the expression of x. Okay? So we have a function f of x. This expression is attached to that f. The x tells you where your blank spot is in the function. Okay, so again, we have an equation, we have a function version of that. What they asked you was, find y when x is 5. Well, another way of writing that is find f of 5. Notice, I changed that x into a 5. That's all. So, I've got 2 times 5 plus 1. So the f told you use this expression, the 5 told you what to plug into that expression. And we get 10 plus 1 is 11. So you could simply say, well, f of 5 equals 11, or remember, these are ordered pairs, inputs and outputs. Input 5, output 11. Either one will work. Sometimes they'll specifically ask you, write your answer as an ordered pair, then go ahead and do so. But if they don't specify, either one of these should be acceptable. Okay? Let's look at a couple more, and then that'll be it for this section. Let's say I give you g of x equals x squared plus 2, and h of x equals 2x minus 9. Okay? So, a lot of times when we name functions, we're using f, g, and h. That's just kind of the standard variables that are used. So, let's say I ask you to find g of negative 3. Okay? Now, what that tells you is, you're looking at the g function. So I'm looking at this. The g function is x squared plus 2. Remember, reintroduce that blank spot. Then, I just plug in the negative 3. That's it. This tells me what expression to use. This tells me what to plug into that expression. Negative 3 squared. Remember, the parentheses mean something. Negative 3 times negative 3 is 9 plus 2 is 11. Simple as that. If you want to write it as the ordered pair, negative 3 comma 11. If I go with h of, let's say, 1/2. H tells me, use this, 2x minus 9. This goes into that blank spot. 2 times 1/2 is a 1. And I get negative 8. Again, this is very, very important on how things are written. Don't overthink it though, okay? All it's telling you is what expression to use and what to plug into those blank spots. Nothing more than that, okay? So this was just kind of a general introduction to some ideas with functions, determining if it's a function or not, domain and range, and then this idea of function notation. We're going to revisit this when we get into chapter 8, okay, and go in a little bit more detail on certain things, but this will all still hold, Okay? So, as always, work hard. Let me know if you have any questions, and I'll see you next time.